Hello everyone, my name is Amir Mahideen and I'm from Group 1, Team Branch, and today I'll be introducing you all branch and bound algorithm. Now, branch and bound algorithm was first proposed by Al Savant and Albert W. Tucker in 1960 when they were carrying out research for discrete programming. And ever since then, it has become one of the most commonly used tools to solve NP-hard problems such as a knapsack and traveling salesman problem. Now, due to the power and generality of the branch and bound algorithm, it is used in so many fields. For example, in logistics, it is used to optimize delivery routes for courier services to minimize travel distances and delivery times. Also in financial portfolio optimization, where it is used to select a combination of investments that maximizes profits while staying within budget constraints. And it is also used for network design, where it is used to find optimal routes in communication and transportation networks while keeping in mind many constraints and costs, and many more. Even to this day, researchers they continue to work on branch and bound algorithm and its variants, adapting the techniques to solve new and more complex optimization problems. Now, what is branch and bound? Branch and bound is a search method, that finds the most optimal solution for optimization problems. Now, from the name itself, it will be very easy to understand how the algorithm works. See, let's focus on the first word, branch. Branching. Branching is the process of breaking down a problem into smaller subproblems. Like dividing a problem into many small branches and then exploring these branches completely until we find the most optimal solution. Whereas bounding refers to ignoring partial solutions that is not optimal compared to others. Like when we are branching into one partial solution and we find out that it is not optimal compared to all these other branches, what do? We restrict it, we bound it, and then we move on to the other small branches. We continue bounding each one of these small branches until we find the most optimal branch or the most optimal partial solution. See, in summary, we branch out, we explore all these subproblems one by one until we find the most optimal solution. Okay. Now, to understand branch and bound even better, let me demonstrate with an example. Now, let's take a look at this weighted graph example, okay? Let's take this S as the starting state and G as the goal state, all right? Now, if you remember, what did I say a branch and bound algorithm does? It first explores all the solutions available, right? So let's start exploring. Let's explore from the starting state, all right? So S, I'm going to put 0 over here because since it's the starting state, its cost is 0. And oh yes, all these numbers, they signify the cost between each state, cost of the path. So S0 is the starting point. Now, what are the options do we have? From S, you can go to A, and from S, you can go to B, right? So let's write that down. S to A and S to B, right? Now, what's the cost? 3 and 6, right? So let's write that next to each other. For B, it's 6. Now, what the algorithm does is it looks at the path that has the least cost. For example, over here, that's A, and it further explores from A, all right? So from A, where all can we go? We can go to C, we can go to D, and we can go to S, right? So let's write that down as well. We can go to C, we can go to D, and we can go to S. Now, when we're going to write down the cost, we are going to add up the cost from the starting state, all right? So that would be 3, all right, S to A, 3, and then A to C, plus 7. So 7 plus 3, that would be 10. And then from A to D is 2, so 3 plus 2, that would be 5. And A to S, that's 3. 3 plus 3, that's 6. Now, what do we do again? Again, we check which one has the least cost. So in that case, D, its cost is 5. It's the lowest, so we further explore D. So where all can we go from D? From D we can go to G, we can go to G, and then from D you can go to B. Let's put B here. From D you can go to E, and from D you can go to A, alright? Let's calculate its cost as well, alright? So D to G, it's 4, 5 plus 4, that would be 9. And then D to B, that's 3, 5 plus 3, that is 8. And then D to E, that is 2. And D to A, that is again 2. Oh, sorry, so 5 plus 2 would be 7. And D to A again, 5 plus 2 would be 7. Alright, now look what happened over here. From D, we have finally reached the goal state. So first part of the algorithm, it's almost over. So what we do, we got one solution where we found our way from the starting state until the goal state, and its cost is 9. So we're going to write over here the best solution so far that we have found costs 9. Okay, so now this is the benchmark from which the branch and bound algorithm will compare. See, I told you that the algorithm, it will explore every solution, right? So far we have reached one solution, but there are still so many other solutions over here. 1, 2, 3, 4, 5, 6, you see? So what it's going to do, it's going to further explore. Look at this. Oh yeah. So the first part of branch and bound. Branch, what it does, it explores, right? Now we are moving on to the second part, bound. So I'm going to explain what bound means in this algorithm. See over here from C, usually it will explore, but right now, since our we already found an optimal solution that costs less than this path, 9, it costs less than 10. What the algorithm does, it does not explore this path. It prunes this path. It bounds this path. Like, it doesn't explore any further. Why? Because its cost is already bigger than the best optimal solution that we already found. So that's what it does. It bounds this path. Now let's go to the next, now let's go to the least path. Check this out. B is 6. It's lower than the best optimal solution, right? So what do we do? Let's see where we can go from B over here, alright? So from B, we can go to S, we can go to D, we can go to E, right? Let's write that down. We can go to S, we can go to E, and we can go to D, right? Now, 6 plus B to S, 6 plus 6, that's 12. And this, 12 is bigger than 9. So definitely that's not the best solution. So what do? We prune it, we bound it. It doesn't explore any further from here. B to E, that's again 6, 12. Again, we prune, we bound it, we do not explore. B to D, 3, 6, 7, 8, 9, 9. Well, we have 9, it's equal to 9, but still, if you go further from here, it will always be bigger than, the best optimal solution that we already found. So what the algorithm does, again, it bounds it. Similarly, now let's go to the next one, S, 6. See, S is the starting state. We already went over here, right? So why are we going to again explore it further? Well, we know that, but the algorithm, it doesn't know. It will still explore it. So that's one disadvantage. It takes a little bit more time by exploring such unnecessary paths, but it is what it is. So from S, where can we go from S again? We can go to A, we can go to B, right? We can go to A, we can go to B. Let's calculate its cost again. 6, S to A, 6 plus 3, 9. Again, wherever we go from A, it will be greater than 9, greater than our best solution. So we again prune it. S to B, it's 6. 6 plus 6, 12. clearly bigger than the best solution we already found, so we bound it again. Now let's move on to A, alright? A, from A where can we go? C, D, S. So C, D, S, right? Now A, we have 7 over here. A to C, 7, 14, clearly bigger than the best. We bound it. A to D, 7, 8, 9. Okay, 9, you know what to do? We bound it, alright? A to S, 3, 7, 8, 9, 10. 10, clearly bigger than the best. We bound it. Now let's move on to E, because E again it's 7, 7 is less than the best solution, right? From E, where can we go? From E, we can go to D, we can go to B, and we can go to G, alright? B, D, G. So we can go to B, we can go to D, and we can go to G, alright? So E to B, we can go 7 to 7, 8, 9, 10, 11, 12, 13, 13. And then clearly bigger than the best solution. E to D would be 9 again, low solution. E to G, aha, check this out, it's just 1. 7 plus 1, what do we get over here? We get 8, and we have reached the goal state. And check this out, this 8, it's lower than the current best solution we already found, right? So what do? We replace this and we put 8 over here. See? So all of these paths, as you can see, we have bounded already, right? And yes, we do have B, but this is 8. If we explore any further, what will happen? It will always be greater than the current best solution. So we have finally found the most optimal solution, which is the least cost of 8. How did we get there? We went from S to A to D, D to E, and then E to G. Alright? We went from S to A to D, D to E, and E to G. So initially we completely branched out, and then once we found the best optimal solution, one by one we bounded the other solutions until we found the absolutely best optimal solution. So yeah, this is how branch and bound works.
Hey all, I'm Shravani and I'm going to cover the applications of branch and bound. So first let us look into the problem statement. It is defined as given a set of cities and the distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. So the two main constraints over here are we need to find shortest possible route and it has to visit every city only once. It has to never turn back to that city again. So TSP has many real life examples. In fact, it is taken from a real life scenario where a salesperson has to move to all the cities starting from his own city and come back to his own city by the end of the day. So let us look how we are going to solve it. First, we are going to generate a state space tree, and we are not going to take all the possible nodes. In fact, we take only the minimum cost node. For solving optimization, we avoid using backtracking as it takes a lot of time traveling to every leaf node. And in branch and bound, we use level order other than depth first search and all things. And we are going to move forward with the node having minimum cost. And while generating the nodes, we find the cost of each and every node. And if we get any node having the cost greater than some upper bound, we are going to kill it and we are going to move forward with the node having the minimum cost. And if we get the minimum cost less than upper bound, we are going to update the upper bound with that value. So let us look into the example to understand it better. So we are going to take this graph and this matrix to solve the problem, and this is the given matrix where we are going to reduce it dynamically. So first we are going to reduce the matrix with row reduction and column reduction. For row reduction, we are going to take minimum row value of each row and then subtracting it from each row. And for column reduction, we are going to take the minimum value of each column and then subtracting it from that column. For example, when we look into the first row, the minimum value in the first row is 10. So we are going to subtract 10 from first row. Like that, minimum row reduction value is 21 and the minimum column reduction value is 4. So the total cost of reduction would be 21 plus 4, that equals to 25. And this would be our matrix 1 after reduction. And the optimal cost value, that is minimum value of the tree, would be 25. We are going to take the cost of node 1 as 25, and we solve this because we are going to find the shortest distance. And it is clear that cost of the tour would be in the 25 in the minimum, that is, it is at least 25. Now we are going to set the upper bound as infinity, and to derive the cost of path while moving from some node I and to some node j, we are going to set all the entries in the matrix, that is, we are going to set ith row and jth column as infinity. And we are not going to move from node j to node I, so we are going to set that also as infinity. To calculate the cost, we are going to reduce this matrix again if it has no minimum value in it after setting the entries as infinity. So let us take this second node. Like if we are moving from node 1 to node 2, we are going to find the cost of this as, we are going to add the optimal cost value plus the cost from moving from node 1 to node 2. That is, moving from node 1 to node 2, the cost would be 10. So we are going to add that, and the cost of reduction. Here all rows and columns has minimum cost as 0, so we are not reducing the matrix. Now we are going to calculate for node 3. Here the minimum value, that is optimal cost, is 25, and while moving from node 1 to node 3, the cost is 17, as we can see in the first M1 matrix, that is node 1 to node 3, it is 17. So we are going to add that, and we are going to reduce the matrix as it doesn't have the minimum value as 0. In the first column we have minimum value as 11, so we are going to reduce it. And while moving from node 1 to node 4, we are going to make the entries of first row and fourth column as infinity, and even here we made them infinity, you can just check. And for this, we don't need to make any row reduction as every row and column has minimum value as 0. And for the fifth row, we are setting as first row and fifth column as infinity, and minimum cost of matrix 5 reduction is nothing. Like second row has minimum value 2, so we are going to subtract it, and in the third row it is 3, so we are going to subtract it again. So the total cost of reduction is 5 in case of node 5. So the total cost of reductions is 5. We need to add that again. So these are the nodes. We are moving from node 1, that is 2, 3, 4 and 5, and in this we are having the minimum value with node 4. So we are going to expand with node 4. Here while moving from node 4, we can move to node 2, node 3 and node 5. Even so we are going to take this M2 matrix and move forward with M2 we are going to take matrix M4 and move forward with that, as we are expanding M4. Here we are going to calculate with M4. M4 has the minimum cost value 25, so we are going to take that as optimal cost here, plus 3, that is, while moving from 4 to 1, we can check in the M1 matrix. While moving from 4 to 1, it is 3, so the cost would be 25 plus 3 and 0, that is, we don't need to do any row reduction as it has minimum value zeros, so we are not doing any row reduction with the node 3. 25 plus 12, and here we are making a same, like we are making the ith rows and jth columns as infinity, and as we can move from jth node to ith node, we are making them as infinities again. With matrix 7 we have reduced it because the minimum value is 11 in first column and minimum value is 2 in row 3. So we are going to reduce this matrix from node 2, 3 and 5. The minimum cost is from node 2. So we are going to expand node 2 here. If we are expanding node 2, we can move from node 2 to node 3 and node 5 because we covered node 1 and node 4. And in this we are going to reduce the matrix because it doesn't have anything, like it doesn't have the minimum value. So we are reducing 11 and 2, and this is our reduction value. And for the fifth thing, we have the minimum cost value as 28. So we don't have row reduction. The minimum cost would be 25. So we are going with 5. And here the whole matrix becomes infinity because we cannot move to any other nodes, and also we are going to kill all the nodes because we have the minimum cost value as 28 and all other nodes have greater values than 28. So we are going to kill all other nodes, and the cost of the tour would be 28 in the minimum, and the path would be 1 to 4, 4 to 2, 2 to 5 and 3 to 1. Next application of branch and bound is job sequencing with deadlines. So first let us look into the general problem statement of this job sequencing. Given an array of jobs having a specific deadline and associated with a profit, provided the job is completed within the given deadline, the task is to maximize the profit by arranging the jobs in a schedule such that only one job can be done at a time. So the main task is to maximize the profit. In branch and bound, it is useful for solving only minimization problems. It cannot solve maximization. So here the task is to maximize the profit. We are going to maximize the profit by converting profit into penalty. That is, we are decreasing the penalty here. So obviously the profit will be maximized, right? So for this, we need to select the jobs, finish them within their deadlines such that the penalty is minimized. Also, time taken for the completion of the jobs varies from job to job. So for this, we are generating a state space tree, and for generating the nodes, we are considering two values, that is cost and upper bound. To calculate the upper bound, we are going to sum up all the penalties except the corresponding penalty of the job. For the cost, we are going to sum up all the penalties till the previous job considered. If we are considering job 2, the cost would be the penalty of job 1. So let us look into the example to understand this better. So firstly, we are going to generate the state space tree, and for that we are naming it as node 1, and initially we are going to take the cost as 0 and upper bound as infinity, which will be updating dynamically. And this is the example with penalty, deadline and time and 4 jobs. While doing the job 1, the cost is 0 because we are not done with any job yet. This is the first job, and the upper bound is the penalties other than job 1's. So that is 10 plus 6 plus 3, that equals to 19. And for N3, the cost is 5 because we are done with job 1. So cost of job 1 penalty is 5. So cost of job 2 is 2, and the upper bound is 5 plus 6 plus 3. Previously we have updated it to 19, from infinity to 19. Now we are updating it to 14 because it is decreased. While doing job 4, the cost is 15 because we have added 10 plus 5, that is already completed jobs. So cost is 15, which is greater than upper bound. So we are killing this node. And same with the node 5. While doing the job 4, we have added penalties of J2, J3 and J1. So it is 10 plus 5 plus 6, that is 21. So we are terminating N4 and N5, that is J3 and J4 over here. And we are moving forward to expand N2 and N3. First, let us consider N2. We are done with job 1. So we are doing with job 2, job 3 and job 4. For N6, cost equals to 0 because the first two jobs are over here and we are not done with any job. So it is 0. And the upper bound is 6 plus 3. We are not considering J1, J2 penalties. So we are considering only 6 plus 3. J3 and J4. 6 plus 3, that equals to 9. It is less than the upper bound 14. So we are updating the upper bound over here. Now considering J1 and J3, the cost equals to 10 because the previously considered job, that is J2's, it is already done. So cost equals to 10, which is greater than 9. So we are killing this here. And now J4, that is node 8, and the cost for this would be J2 and J3 penalties, that is 10 plus 6, it is 16. Cost equals to 16, and this is greater than upper bound, that is 16 is greater than 9. So we are killing even this over here. Now let us expand N3. J2 is already done, so let us expand with job 3 and job 4. For node 9, cost equals to 5 because we have we are taking job 1's penalty, so cost equals to 5, and the upper bound equals to 5 plus 3. We are taking penalties of job 1 and job 4. Now N4 with N10 with J4, the cost would be 11, taking J1's penalties, so it is 11. So we are killing this node as it is greater than the upper bound. Now the upper bound is set to 8. This is the time where we check with the deadlines. Here, when we expand J2 with J3 and J4, as we are done with J1 and J2, when we expand when we expand node 6, it is moving from J1 to J2. Now this N6 is alive. So to do job 3 and job 4, these cannot be done within the deadline, as the deadline to complete J1, J2 and J3 time required is 4 hours, and to complete J3 job we only have 2 hours. So this cannot be completed within the deadline. So we are killing this node. And to do J4, we have to complete J4 within the deadline with 1 hour time. This cannot be done, so we are killing even this node. Now let us look at J3, and from J2 we are moving to J3, and now from J3 we are going to J4. To complete J4, we need J2, J3 and J4. Even this cannot be completed within the deadline. So this is also killed. So we cannot move. So these leaf nodes become infeasible as the jobs cannot be done within the given deadlines. Hence we are done with the tree because these leaf nodes cannot be extended further because they are becoming infeasible with the deadlines. So we get minimum penalty equals to 8 and the minimum cost equals to 5 from node 9. Over here we are getting cost equals to 5 and upper bound equals to 8. So upper bound is taken as penalty and minimum cost is taken as 5. The jobs will be doing her J2 and J3 as they can be completed within the deadline with minimum cost and minimum penalty to maximize the profit. Like here we are minimizing the penalty. So obviously profit is maximized. And penalties we need to pay by doing jobs J1 and J4 would be 5 plus 3, it is 3. And the penalties we saved without doing jobs J2 and J4, that is 10 plus 6 is 16. So the whole problem is here, like we have solved it by not doing the jobs J2 and J4, because the main task is to maximize the profit. We have maximized the profit by decreasing the penalty by doing only limited jobs within the deadlines. So we have minimized the penalty. This is the main aim of the problem. Thank you.
Hello everyone, my name is Ahmed Wakadi, and today I'll be discussing a research paper titled School Bus Routing Based on the Branch and Bound Approach, authored by Kumar and Jain, published in 2015. I truly apologize if I butchered the name. Before we approach this research paper, I'd like to discuss something about the 7 steps of branch and bound. The first step is initialization. Second step is choosing region. Third step is lower bound. Fourth step is upper bound. Fifth step is pruning. Sixth step is check region. Seventh step is branching. As you can see in this image, lower bound, when answered with a no, it will return to the second step. And when pruning is answered with a no, it will return to the second step. Also, you could see how it goes here. If check region is answered with a yes, and the global maximum of the region, any more subregions, and if answered with a yes, it will return to choose region. These are very important later on for the research paper and how the branch and bound algorithm will be approached. Now, vehicle routing. Vehicle routing is a problem in which vehicles are located at a central position, has to serve the customers located at a different position in the city. We'll look at a specific problem inside the domain, the school bus routing problem, and how the branch and bound approach can help solve it. The traveling salesman problem is similar to the school bus routing problem. In layman's terms, it initials buses operating within set time frames, picking up children at defined places and returning them to central point, which is the school, normal school system. 3 main elements distinguish school bus scheduling: reducing the overall cost of operating school buses, ensuring that the service demand is met, keeping a fair and dependable scheduling system for all students across several schools. The purpose of this research paper is to show how to maximize the total school bus trip. The paper provides us with an example of school bus scheduling as well as a solution to the problem. Here's the example. In this example, we look at 3 schools, each with 4, 3, and 4 journeys. The author also provides us time constraints for each school within which pupils must arrive. A single bus is scheduled for both journeys if it can accomplish both trips without exceeding the time constraint. Consider the school time windows as T1, T2, and T3, where T1 is smaller than or equal to T2, and T2 is smaller than or equal to T3. School 1 has 4 bus routes. As you can see here, R1, R2, R3, and R4. School 2 has R5, R6, R7, and School 3 has R8, R9, R10, and R11. Now, various schools as shown in the diagram require various buses to operate on distinct routes. As long as the school time windows and bus capacities are not violated, the optimization technique compromises assigning one bus to many routes. The optimization provides various benefits. One of them is reducing the overall expense of the journey, and the second one is shortening the entire journey time. The school bus problem is further subdivided into the following subproblems. Selecting buses from the available bus fleet, homogeneous, and heterogeneous, selecting a bus stop from a list of possible stops, designating specific bus stops for students, assigning bus stops to certain buses, establishing bus lines. And in here, we could see all of these applied. How everything changes. Now school 1 has a connection to the route 8, and school 2 has a connection to route 9, and school 3 has a connection to route 7 and route 4, and also school 1 has a connection to route 5, and school 2 has a connection to route 2. Now you can see them, they're all intertwined. Now, the mathematical notations. Formulation of homogeneous bus fleet model. We look at the homogeneous fleet problem here. Homogeneous buses are that are consistent, meaning they have the same capacity and priority. The notations listed are used in this context. The table contains all list of all other needed terms. In here we can see all the needed terms that are going to be used in the formulations or the calculations. The notations here, for example, is I, J, stop index, S is stop of stops, and everything else can be read. Now, as we remember, branch and bound has constraints. So this is very beneficial for branch and bound. So we read the constraints are as follows. The first constraint, all buses should be assigned to each of the stops. Second constraint, numbers of buses arriving at a stop should be equal to number of buses departing from that stop. Third constraint, it states that when we serve stop J and stop I, then services start to stop J should be equal to or greater than service start time of stop I plus the time taken between the two stops. The fourth constraint, it shows the constraint of the time window. Now, we will approach on how the branch and bound is going to be implemented in this school bus writing problem. The initialization step. Set the lower bound and upper bound to their default values first. We must use the Hungarian algorithm to solve it. If we discover that the lower bound solution is possible, we will terminate the method because it is the best solution. Otherwise, set the lower and upper bound to AU L times AU equal to function of BU. Now, AU is A upper bound, A lower bound, and this is also A upper bound, equal to the function of B upper bound, or A lower bound equal to function B lower bound. Now, stopping step of if our problem list is empty or the calculations time is up, the best objective value will be returned. Else, take from list and go to step 3. Remember, step 3, the branch and bound steps. Now, branching. Branching, we will use the lower bound assignment problem to find an infeasible link from 1 to 2. Then we'll divide it into 2 sections. Now, infeasible link between 1 and 2, the branching into 2 parts, does not contain the link CL, does not contain the link. Now, bounding 1, set prohibited assignment problem, lower and upper bound, and solve them using the Hungarian algorithm. If lower bound of the prohibited assignment problem is feasible to the original problem, then if B upper bound is bigger than the function prohibited assignment problem lower bound, B upper bound is equal to function prohibited assignment problem lower bound. Proceed to step 5. Else, B upper bound is bigger than F upper function prohibited assignment problem lower bound. Go to step 5. Else, add the lower bound value to partial list and go to step 5. Again, Steps, branch and bound steps. Bounding 2. Bounding 2, set the values of CL upper bound and CL lower bound. Then we are going to solve it using Hungarian algorithm. If lower bound of this combined assignment problem is feasible to the original problem, then if B upper bound is bigger than the function combined assignment problem lower bound, B upper bound is equal to the function combined assignment problem lower bound. Proceed to step else. B lower bound function combined assignment problem lower bound. Go to step 6. Now we go back. Else. Else add the lower bound value to partial list and go to step 6. Now, bounding 3. Delete all the nodes whose value of lower bound is greater than that of upper bound from the partial problem list. Now go to step 2. Let's see this in an experiment that the researchers did. As you can see here, these are the files, the schools, the number of trips, the number of students. In the first one, the homogeneous buses, we will see that the number of buses 1 and the total distance traveled is 4, and it took them a time of 150. We can see that every time 2 buses 620, 3 buses 1000, 4 buses 1200. So it's not really good. But in the assignment problem using the branch and bound, we can see that in 4 buses it was able to reach a time of under 1 millisecond. And in 10, under 1 millisecond. In 11, under 1 millisecond. But then in 45, with a total distance traveled of 1,273, which is still a lot more of the total distance traveled from the homogeneous buses, it was able to reach 1 hour. In 65, 3,116, above an hour, which is still good. But there seems to be a problem. The branch and bound plays a crucial role in optimizing school bus routing problems, aiming to minimize costs and traveling time while adhering to specific constraints. However, its feasibility diminishes as problem complexity grows. So, if the problem grows more and more, I don't think branch and bound will be able to catch it.
Hello, everyone. My name is Amal Anu, and today I'd like to go over the paper Fast Branch and Bound Algorithms for Optimal Feature Selection by Peter Somol, Pavel Pudil, and Joseph Kittler, published in July 2004. Now, before I get into the paper itself, I'd like to go over some details about the authors. Peter Somol received the Master's in Science and the PhD at Charles University in Prague in the Czech Republic. He is with the Department of Pattern Recognition at the Institute of Information Theory at the Academy of Sciences of the Czech Republic and is also currently the AI Research Director at Avast Software. Pavel Pudil is the Dean of the Faculty of Management at the Prague University of Economics and is also with the Department of Pattern Recognition at the Institute of Information Theory at the Academy of Sciences of the Czech Republic. He is also an IEEE member. Joseph Kittler is a professor of machine intelligence and director of the Center for Vision, Speech, and Signal Processing at the University of Surrey in the United Kingdom. He is also an IEEE member. Now, these 3 authors that came together and created this paper primarily to optimize the branch and bound algorithm as seen here. This is just a basic branch and bound example. But the authors base their investigation of optimizing branch and bound not on the traditional method that you've already learned that is displayed here, but rather an improved branch and bound method. Improved branch and bound, which the paper refers to as IBB, takes advantage of a common characteristic of the tree. As the tree is fleshed out, different nodes can have different numbers of successors. So as we can see here, node branch 3 has 2 successors, while branch 4 has 1 and branch 5 has 3. While searching through the tree, you could spend a long time looking through the dense parts of the tree, while the simplest parts lay untouched until the end. So for example, because you can explore these trees in largely any order with basic branch and bound, if you had looked through tree 5 first, you would have to go through the entirety of all of the branch 5 first. You would have to go through the entirety of all of these branches before you would get to branch 3, where the actual answer is here. With IBB, the sparse parts of the trees are explored first, and the dense parts are left for later. But how do we determine which branches are sparse and which are dense without actually exploring them? This is where the improved branch and bound algorithm comes in. The improved branch and bound algorithm, IBB, uses what's called a criterion value decrease. Essentially, it's you take the current bound here. So for example, for the first layer, it would be the current bound would be 15, and then you subtract one feature from it to get the next bound, and then the difference between the current bound and the next bound is your criterion value decrease. Or in more simpler terms, the criterion value decrease is simply whichever feature you have removed from that particular set. So for example, 15 is the current bound, and if you remove 3, you get 12. 15 minus 12 is 3. You do this for every single one of these of the features of that layer. Those features with the smaller criterion value decrease lead to more sparse outcomes, which the paper refers to as quote-unquote bad, while those with greater criterion value decreases, which the paper refers to as good, lead to denser outcomes. So what we do is we arrange the tree so that the bad features are on the right and the good features are on the left. This, for example, with this particular example, you would swap the positions of branch 4 and branch 3. The branch 4, which is a greater difference and so is good, is in the middle, while branch 3, which is a lesser difference and so is bad, is off to the right. Once you have arranged the tree in this way, you would explore the tree from right to left, exploring the bad branches first and then working your way to the good ones. In this way, you can quickly trim the bad branches of the tree before you get to the denser good the sparse bad branch of the tree before you get to the denser good branches. Of course, and in doing so, you can get the correct answer in one simple exploration rather than having to explore the entire tree. And once you get the good answer, you can simply cut off all of these branches. Of course, both regular branch and bound and the IBB algorithm have their flaws. Neither method guarantees that enough branches will be cut off to keep the total number of computations lower than an exhaustive search of the tree. The nodes, especially the nodes closest to the roots of the tree, are often the most numerous and can't really be quickly trimmed because you'd have to explore more in order to decide whether they're worth trimming. Which leaves the algorithm to essentially get bogged down and waste time evaluating the less promising nodes closer to the root here. In addition, with the IBB algorithm, the number of computations that are needed to order the nodes from bad to good are significant, and there, again, is no guarantee that it will be more computationally efficient than a basic branch and bound algorithm. What the authors have decided to do is specifically remedy the issue specific to IBB, namely the number of computations needed to sort the nodes, by using a simpler prediction mechanism. They call this method the branch and bound with partial prediction algorithm, or BBPP. This is the diagram that they have shown they have created to essentially display how BBPP works. Now, if this looks complicated, don't worry. This entire bottom portion is just basic branch and bound. The actual relevant portion is this. Now, what this does is simple. Instead of calculating the criterion value decrease for each feature at the current level, BBPP instead predicts the criterion value decreases instead and orders them in ascending order using the predicted values. Now, a quick note, this diagram mentions that they're sorted in descending order, whereas the actual text of the paper mentions ascending order. I have chose to go with ascending because that fits more with what the original IBB algorithm does, which is evaluate the smaller decreases and then the bigger ones. After it predicts these values and orders them, BBPP takes the first few predicted values from the order sets and calculates the true criterion values and explores the tree using that. It stores this prediction information using two vectors. Vector A, which stores for each feature the average criterion value decrease from removing that feature from the current candidate subsets, and vector S, which stores for each feature the number of criterion value decrease evaluations carried out. This seems rather complicated. Vector A essentially just stores the average criterion value decrease. So for example, if you remove a feature from this subset and another subset and another subset, you would average those out and just store that specific value. And for vector S, you would just store the amount of times you have actually calculated the criterion value decrease for that specific feature. So again, going back to the example, this subset, the next subset, and the next subset, that's 3 subsets. So the vector S would store for that specific feature 3. Whenever a feature is removed from the set and computes that feature's actual criterion value decrease, the prediction vectors are updated in order to essentially keep the prediction mechanism self-learning. Now, this might seem, again, kind of complicated, but essentially what this can be boiled down to is branch and bound with partial prediction does the exact same thing as improved branch and bound in that it uses the criterion value decreases to simply sort from left to right which branches this should do. But instead of calculating the criterion value decreases, it simply predicts the criterion value decreases, sorts them, and then from there calculates them properly in order to get the actual answer. The authors also propose another algorithm that they call the fast branch and bound algorithm, or FBB. FBB builds off of BBPP by using a stronger prediction mechanism with the goal of further reducing the number of computations used. Unlike BBPP, which just uses its predicted criterion values as a guide to determine which actual criterion value decreases to calculate first, FBB treats computed and predicted criterion values equally. So for BBPP, we saw that they would predict the values, sort the tree using those values, and then actually properly calculate them. In this case, they don't calculate them at all. They just predict and just use the predicted values. Again, FBB treats computed and predicted criterion values equally, with the caveat that the prediction itself is only used in certain circumstances. In order to keep any errors to a minimum, it only uses the predicted value in certain circumstances instead of using it all the time. For example, if the predicted value is significantly greater than the current bound, then it is assumed that the actual value would also be significantly greater. So the actual value is not computed. They don't bother with it. We save ourselves some computation time. If the predicted value is greater, but still close to the bound, which there's no real hard and fast rule for how close is too close, that's generally up to you, then the actual value could be greater or lesser than the bound, so it is computed. If the true computed values are lower than the bound, then the branch is trimmed, as with regular branch and bound. FBB also uses the same 2 vectors, A and S, that BBPP uses. In addition, the predicted value is only used if the number of times the criterion value decreases computed is above a predetermined minimum. So what that essentially means is they don't use in addition to all the other exceptions I mentioned, they don't use a prediction value if the mechanism has not learned enough. If the mechanism continues to build off of information and has learned enough beyond a predetermined minimum, which again, beyond a predetermined minimum for that specific feature, which again is up to you, the creator, the user, then it's not used. Otherwise, obviously, the algorithm computes the actual value. To distinguish between computed and predicted criterion values, because we don't want to use the predicted values if they're not reliable, a type vector is used for each node, where for each node they are flagged with either P for predicted or C for computed. I unfortunately don't have a diagram to show you about this. This vector, the contribution vector, is only updated if both the current node and its parent have both been computed. In this way, the algorithm does not use predicted values until the prediction algorithm has been updated to be more reliable. And once it has, the algorithm relies more and more on prediction versus actual computation. Neither of these two algorithms are without issues forever. Both of them use prediction mechanisms which are based on heuristic assumptions, so they can't be expected to work flawlessly. FBB and BBPP are most likely to become more effective than IBB once the prediction mechanism has had ample information to learn and accurately predict criterion values. But until it has, it could make mistakes. FBB is a straight upgrade to BBPP if the prediction algorithm does not fail, but BBPP is less reliant on the success of the prediction algorithm. BBPP only uses this prediction algorithm to decide in what order each branch should be explored. So if the prediction algorithm makes a mistake, no biggie, you'll lose some time, but you'll still explore them. FBB actually uses the predicted value in calculations, as well as deciding which node to explore first. So if the prediction algorithm is wrong on something or it makes a mistake, then you will just get a straight up incorrect answer, which is why there are so many safeguards to make sure that predicted values are only used if they can be trusted. Of course, regardless, even with strong prediction inaccuracies, both FBB and BBPP, especially the latter, outperform improved branch and bound and the traditional branch and bound. Both algorithms do spend additional time maintaining the prediction mechanism, adding and modifying the vectors and learning the prediction mechanism learning, but that time spent is largely negligible compared to the time saved by the algorithms compared to their more traditional counterparts. It should also be noted that due to FBB's reliance on predictive values, it cannot evaluate criterions where knowledge of the previous node is needed to calculate the current node. It cannot evaluate recursive criterions. In the interest of time, I will not be exhaustively going over the experimental results of the algorithms displayed in the paper. There are quite a few experimental results, both simulated and real data experimental results. And if you are interested, I do recommend you check it out. I have simply shown a part of the experimental results displayed. Just to give a quick summary. On the whole, the experimental results seem to support the author's claims of the efficiency of their algorithms. Here we can see a non-recursive evaluation of FBB, BBPP, improved branch and bound, basic branch and bound, and a normal exhaustive search of the tree. And here we can see a recursive one, which does not feature FBB because as mentioned, FBB cannot do recursive criterions. Two things are notable from the experimental results. While FBB is definitely an improvement over BBPP, they are very close to each other. And depending on your preferences, it may be more advantageous to forgo FBB in favor of BBPP, as BBPP is a bit more reliable, or far more reliable. Also, with extremely large or extremely small feature sets, as we can see here, the difference in computation times between FBB, BBPP, improved branch and bound, basic branch and bound, and the exhaustive search are largely negligible. Now, you'll probably almost never come across a problem where the feature subset size is 1 or 3 or whatever. But like, say 5, 7, or even like later 27, 29, when you have rather small feature subset sizes or large feature subset sizes, it may just be better to forego these and use a more traditional, less error prone mechanism. As again, FBB and BBPP may not necessarily be the easiest or more efficient option. But if you're, for the most part, FBB and BBPP are far more computationally efficient and faster than all of these other algorithms.
Hello everyone, my name is Ashish Avdani and today I'm gonna discuss on paper branch and bound algorithm with application to robust stability by Le Ravenbaum, Damascus Knoll and Bray Akren. Pardon for the mispronunciation of the words. So to begin with, I would like to give a brief introduction of the paper. In this paper, we delve into the challenges posed by uncertainties in mathematical models of physical systems and stress the significance of maintaining system stability and performance. Despite this uncertainty, to address this issue, researchers are actively developing methods like new singular value and a branch and bound algorithm to access or quantify system robustness. This technique are crucial for ensuring the real world system perform well even when mathematical models are impactful. The paper mainly discusses how the mathematical model of physical system get affected by uncertainties like unknown parameter and changes over time. It also emphasizes the importance of ensuring system stability and performance despite these uncertainties. Researchers are developing methods like new singular value and a branch and bound algorithm to analyze quantify system robustness. So basically they are trying to analyze and quantify the system's robustness to further increase the efficiency of branch and bound algorithm. These methods will help engineers to ensure that system works well in real world conditions even when the mathematical model are not perfect. The goal is to access its performance and robustness in presence of this uncertainty. So there are main three criteria to discuss. There are one, the worst case H infinity performance. This criterion computes the maximum possible performance degradation represented by H star that can occur due to uncertain parameters within specified range. And the next is robust stability. The paper aims to figure out whether the system remains stable across a given parameter range. This involves maximizing the spectral abscissa of system matrix over parameter range with stability confirmed if alpha star is negative, and the third is distance to instability. This criterion seeks to find the largest variation in the parameters under which system still is stable, assuming it is initially stable at the nominal parameter values. Then we find out local trust region optimization. This analysis involves complex optimization problem due to the uncertain parameters, making them computationally challenging, with some being NP hard. We use a local optimization technique trust based on non-smooth bundling trust region algorithm to compute a locally based solution alpha of which given a lower bound alpha and alpha star. Here the focus is on local trust region method. Trust, which plays a crucial role in branch and bound approach for computing alpha star. The existing method used by Balakrishnan calculates lower bound by evaluating alpha at center of each parameter box in the list and taking maximum these values. The first bound is updated often but may not be fully correct initially. The trust method, on the other hand, supplies significantly more correct estimates of alpha, making it helpful for pruning in the branch and bound algorithm. When the trust starts with the first guess sigma 0, it finds a locally based solution such that alpha is a subset of A and sigma star is greater than or equal to alpha A of sigma 0. This locally based value becomes the lower bound, and the branch and bound algorithm uses this monotonic property. By starting trust at the center of parameter box, we can easily improve upon the first lower bound, enhancing the efficiency of the algorithm. So now we are going to start a new algorithm which is based on branch and bound to compute alpha star in the program. This algorithm is branch and bound method designed to compute value of alpha star in optimization program, which stands for largest spectral abscissa of system matrix over a parameter range. It starts by using a local solver trust to compute a lower bound alpha on alpha star. The current parameter vector is set as increment solution. Initialize Then it initializes a list with the entire parameter range from -1 to 1 is to m. Then it iterates while there are elements in L to evaluate. After evaluating, it selects an element from L based on a ranking criterion. Then it applies a pairing test to check if the selected element can be paired or removed based on pairing tolerances epsilon. If pairing is possible, remove the element from L. If not paired, the element is replaced by two successors in L. Then it calls the local solver within the successor to update the lower bound and increment solution. After that, it updates the ranking of elements in L using ranking subroutine R. This process continues until L becomes empty. Finally, the algorithm returns the computed value of alpha star D and the corresponding parameter vector sigma. So, this branch and bound approach efficiently explores the parameter space to find largest spectral abscissa while pruning unproductive branches and updating the increment solution when necessary. So we have one more algorithm which which is branch and bound for D star in the program. This branch and bound approach efficiently explores the parameter space to find largest spectral abscissa while pruning unproductive branches. This algorithm is designed for optimization problem with a given tolerance threshold which is greater than 0. It employs a local solver called trust to compute an upper bound and an increment solution sigma. It iteratively refines the solution by considering a list of boxes covering specified range. The boxes are ranked using a subroutine called R in each iteration. It selects the top ranked boxes, applies a pruning test, and determines if it can be pruned based on given tolerances. If pruned, the box is removed. Otherwise, it's divided into two successors, and the local solver is used within them to update the upper bound, increment, and the list. This process continues until the list is empty, returning the final upper bound and increment solution sigma. So This was about the paper. Now, I would like to conclude and explain briefly what we have seen or presented in today's session. In the branch and bound algorithm, a systematic search is conducted by branching out to explore various paths while continually bounding and pruning suboptimal solutions. The goal is to find optimal solution to a problem. This iterative process efficiently narrows down the search space and ultimately leads to conclusive and optimized result. We have also discussed the traveling salesman problem and the research by Peter Summel, Pavel Buril, and Joseph Gittler, pardon for mispronunciation, presents innovative branch and bound algorithms such as improved branch and bound IBB, branch and bound with partial prediction BBPP, and fast branch and bound FBB, aiming to enhance feature selection. While these algorithms offer computational advantage over traditional methods, their effectiveness is subject to prediction accuracy. Depending on specific problem character size, choosing between fast branch and bound and branch and bound partial prediction may be preferable with negligible differences in small or large feature subset sizes. The branch and bound algorithm applied to the school bus routing problem offers an optimal solution for smaller instances. However, as problem size increases, its computational time becomes impractical. Therefore, it may not be feasible for large scale school bus scheduling problems, needing to exploration of alternative approaches for such scenarios. These are the references that we used for our presentation, and thank you everyone for patiently listening to this presentation. And on behalf of all my teammates, I would like to extend my thanks to everyone. So, thank you everyone. Have a good day.